All right, welcome back for side 2 of our notes for nonlinear systems. Elimination works the exact same way for nonlinear systems as it did for linear systems. Our goal would be to try to cancel out one of our variables by getting coefficients that are equal and opposite. So here you've got a couple choices. You could cancel out either the x or the y. I am going to select to cancel out my x values because I can quickly and easily turn a 2 into a -4. I'm going to do that by multiplying by -2. So that equation would read -4x squared minus 6y squared, and let's see, -166. On the bottom, let's just recopy. We're not editing that one at all. If I had chosen to cancel out the y's, I would have had to edit both equations, which is why I chose just to work with the x's. Now, when I go ahead and add my equations together, right, I'm going to cancel out my x squared terms, and I'll be at a point where I could solve for y. I'll have one equation with one variable. And if I add that together, I get -200. Divide out the -8, and you're at 25. So I get y equals, be careful, when you have a squared equation and you're taking the square root of both sides on an equation, you're going to actually get 2 solutions, plus or minus 5. Then we've got to go back and we've got to pick an equation to plug back into to figure out our corresponding x values. So I just went back to the first one. Either one is fine. I just like the first because it doesn't have any negatives in it. And I'm going to plug in to 2x squareds, right? I'm solving for x still. I'll have +3. Now here, if I plug in positive or negative, it really doesn't matter because they're both going to square out to be a 25. So we're just going to pop in 25, and I won't have to do the equation twice for each of the individual x solutions. So that's going to give me 75, and if I subtract that over, I'll have an 8, and divide out by 2. And here I get 2 more solutions. So you've got to be careful. You've got to think about this really carefully. When y is 5, I could be positive or -2. So my list of solutions is actually 4 solutions long, right? If x is 2, I could be a positive 5, right? Or if x is -2, I could be a positive 5. And likewise, when I plug in -5, I can get positive or -2. So that's going to generate 2 more solutions, -2, -5, or -2, positive 5. So this particular problem has 4 solutions. This would be some sort of an ellipse and some sort of hyperbola. So what's probably happening is that you have your 2 branches of your hyperbola plus your ellipse. We don't need to graph them out, but that's where the 4 solutions are all coming from. I know it looks like we took a lot of space here, but we're in luck. The second one, letter B here, is pretty short. I just wanted to make sure we went over this idea of no solution versus infinite solution. So on this one, to me, again, this one's perfectly set up for elimination, and you could go for either the x's or the y's. I elected to try to cancel out my x's, so I multiplied that top row by 2. That would give me 2x minus 4y equal to 6. And I'll just recopy that second row because I've already accomplished my equal and opposite in terms of x's. The thing is, I got really lucky because I also canceled out all the y's. So on the left-hand side, everything is canceled, and I would have 0 equals to 7. A few of you asked me about this in the activity yesterday. When you get a nonsense statement, 0 equal to 7, what that really means is, are there any combinations of x and y that you could ever plug in that would make this true? And the answer is no. 0 is never equal to 7. It doesn't matter what selections you make. So the answer here would be no solution. If you don't get a nonsense statement, so here just as an aside, because it didn't work this time, but if you had gotten something that was an absolute true statement, 0 equals 0, 2 equals 2, right? If you get a true statement, then the answer to this would be infinitely many solutions. It doesn't matter which x's and y's you choose. There are an infinite number of solutions that would make that true. You have to be really careful. Some kids get this confused with all real numbers. That's not true here because the combinations matter, right? There are infinitely many solutions. They would just happen to be all the points that live on this line and infinitely many solutions that live on this line. They're multiples of each other is what's happening in that case. Anyways, so a nonsense statement, no solution, 0 equals 0, or a true statement, infinitely many solutions. Last but not least, I just threw one on to remind you that sometimes you might have to edit both equations. So here, there's no easy way to turn a 2 into a 5 or a 3 into a 4. So we're going to have to edit both equations. I decided that I wanted to try to get rid of my y variables. That would mean that I needed to multiply by 4 up top and by 3 on the bottom. I chose y's because that kept me from having to work with negatives. They're already opposite. I just need to make them equal. So I would rewrite the first line as 20 times x plus 12 times y equal to 36, and that bottom line as 6x minus 12y equal to 42. That way, when I add these two together, right, my y values will disappear. I can eliminate that variable. I'm left with 26x, and on the right-hand side, I have 78. And if I divide out my 26, I will end up with a 3. Don't forget, you've got to go backwards and solve one of the two equations. It doesn't matter which one. I elected to go back to the first. 5 times 3 plus 3 times y has to equal 9. So 15, take that away from 9, I get a negative 6. And my y is negative 2. You should be writing your solutions as coordinates. So there we go. This last equation, or this last one, I just wanted to show you at least one story problem. It actually could have been on yesterday's because this one is two linear functions. So here we have a supply and demand equations. Demand and supply equations for this new personal digital assistant, kind of like a smartphone before smartphones existed, were given by these two equations. So these are the price equations. The equilibrium point, that's just a phrase from econ that you might have either forgotten or not seen yet, but that's where your supply is equal to your demand. Right? So we'll assume that they're going in order. If this top one is the price point for the demand and the bottom one is the price point for the supply, equilibrium would be where they are the same. You have a couple of choices here. You can set this up either with substitution. They're both equal to P, so they're both equal to each other. Or you could set it up with elimination. This one would be really easy to eliminate. If you didn't want to work with the decimals, in fact, you could go ahead and multiply that top one by 2. Or you could have just done the negative and added them together because the p's already match. So I rewrote mine as 2p equal to 300 minus 0.000, how many are there? 4? 2x. I just didn't want to work with the decimals anymore, so I elected to get rid of the x variable. And then I'm not going to edit that bottom equation because I was looking for those equal and opposite variables. But again, you could have done elimination of the p variable. You could have done this with substitution. There's multiple ways that you could solve this problem, and you'll still get to the same answer. So now when I add them, 3p is 360, or my p is $120. Now I got to go back and reread the question, of course. Find the equilibrium point for this market. The equilibrium point would be both the price and the number of units sold. So we're going to go back and just determine that if P is equal to 120, then that should also be equal to 60 plus 0.0002 times x. And I could quickly subtract 60, divide out the decimal. You'd obviously need a little calculator here. And you would have 3 million units. So our price point would be $120, selling 3 million units. Tomorrow, we'll be practicing in class with these nonlinear systems. And on Monday, we'll add in some more of the story problems to work with here.